In LeetCode problem 17, letter combinations of a phone number, we're not just decoding keypad buttons. This mirrors real systems like predictive text, layered menus, and recursive queries. It sounds simple, match digits to letters, but as digits pile up, combinations explode. That's a performance hazard in real apps. So how do we avoid clunky nests of loops and build something that scales? Let's break it down. Let's kick things off with a brute force approach. We'll build every letter combo the old-fashioned way. No tricks, just raw nesting. Time to translate that idea into code. First up, handle the simplest edge case. If the input is null or empty, there's nothing to generate. We return an empty list. We set up our digit-to-letter mapping using an array where each index lines up with a digit and the value holds its letters. With the mapping in place, we prep our result list and capture the input length so we can customize the logic. If there's just one digit, we walk through its mapped letters and drop each one directly into the result list as a standalone string. With 2 digits, we pair each letter from the first group with each letter from the second, building all 2-letter combos. For 3 digits, we add a third loop, now forming every possible trio by combining one letter from each digit group in order. And if we hit the full 4-digit limit, we bring in a 4th nested loop to generate every valid 4-letter combo from left to right. Once all combos are built based on how many digits we were given, we return the result list we've been filling. This brute force method runs in big O of 3 to the n times 4 to the m. With 4 digits, that's up to 256 combos. Manageable, but it scales poorly. It also eats the same big O space to hold results. Since we're hard-coding 4 digits, it works, but it's not future-proof. And heads up, if input grows, this won't cut it. So how do we reduce the overhead? Instead of hard-coding loops, we'll build combos step by step, like hopping lily pads across a pond. Let's shift to an iterative approach. We kick off with the same base case. If the input's null or empty, we skip the rest and return an empty list. With valid input, we define the digit-to-letter mapping, just like on an old-school phone. The array lets us index into it quickly with each digit. To build combinations, we use a queue. Starting with an empty string, we'll stack on letters as we work through each digit. We process each digit one at a time. For each, we grab the letters it maps to by converting the character to an index and accessing our array. Before diving into those letters, we lock in the current queue size. That tells us how many partial combos we've built so far. Now for each of those existing combos, we dequeue it and try appending every letter tied to the current digit, adding the new combos back into the queue. After we've processed all digits this way, we convert the queue into a list and return it. That's our full set of combinations. This runs in big O of 3 to the n times 4 to the m, same as brute force, but we avoid rigid nesting. 4 digits still means 256 operations, but the queue gives us cleaner structure. It uses more memory, but it's easier to follow and scales more flexibly. We're still generating every combo, but we're not optimizing the path or pruning any branches. Time to take things up a notch. First, we lock in our digit-to-letter mapping as a constant lookup table. That keeps our access fast and avoids messy branching logic. Next comes the main method. We create a list to store all final combinations as we build them. We check for the empty input case again, and if there's nothing to process, we return our blank result list immediately. If the input's good, we kick off our recursive backtracking process, starting at the first digit. After all recursive paths have been explored, we return the list of completed combinations from the main method. Inside the helper method, if we've hit the end of the input string, that means the combo is complete, so we add it to the result list. If not, we fetch the letters mapped to the current digit. That gives us our set of branching options at this level. We loop through those options, append each letter to our current combo, and recurse forward. After each call, we backtrack, removing the last letter to explore the next path. Backtracking gives us the same time complexity, big O of 3 to the n times 4 to the m. But memory use drops to big O of n, just the depth of our recursion stack. It's leaner and cleaner, and interviewers love it for how well it scales and models recursive trees. So we began with brute force, clear but rigid. Then we shifted to BFS with a Q, gaining structure and flexibility. But backtracking is the real win. Clean code, smarter memory use, and scalable logic. It's not just a LeetCode pattern, it solves real recursive tasks like parsing, UI trees, and predictive input. That's why it's a go-to in interviews. To sharpen your skills, look for problems where backtracking or BFS unlocks smarter solutions. And keep going. Optimization is always just one duck step away.